The web wants to buckle, fine, buckle. I don't care. But I'm gonna continue to use you to carry the load. You can't die just yet. You must stay with me even if you buckle, right? So that's we call the post-buckling strength. We can have this if we can provide the proper stiffness, okay? Or the compression strut, just like the strut and tie model. Okay, now, this is a new spec. Now when it involves the shear strength of web with tension field action, they now call it CV number 2. Back in the old days, they only have one CV. So there was no CV1, no CV2. Now they have 2 CVs. Because, I don't know. And in the previous spec, we only had this formula. Because they would just limit that, okay, you must satisfy this condition and that condition for the plate girder. When you satisfy these conditions, you can have the post-buckling strength. And you can see that if you look at this formula, when we have this formula, if I erase this, it's the same, right? It's 0.6 Fy multiplied by the area then CV. But if the web is so slender, the CV is very small. But then again, because of the post-buckling strength, the tension field action, you have an extra term. And this term is induced by the tension field action. A few years ago, we have this one formula and we have these limitations. But now, they say you don't have to satisfy these conditions anymore, but if you cannot satisfy these conditions, you have the new formula. This is somewhat related to the old one, but just with more terms. I don't know. I have never used it, which is the first time I see it. But the tension field action term is different. That's all. The nature is pretty much the same, right? The shear strength plus something extra for the tension field action. Okay? You may do this one day, you may not. But now you know the crucial characteristics of the plate girder. Okay? What makes the plate girder stands out is that the web is slender and you need to know how to utilize the tension field action. Otherwise, it cannot carry the shear. And you see, the council wanted me to learn this in the undergrad level. It's not possible. It generally takes me like 3 weeks, yes, to, convey all this to graduate students, right? And CV2 now, it's this bunch. Now, you can see the difference is that for CV1, that's just this and that. No, this one. So this limit is gone in CV1. Back in the old days, they just one set of formulas with this limit. And now they just remove this for CV1. I don't know, I haven't read the commentary. If you want to know the history of how formulas have been developed, it's always available in the commentary section of the spec. Both for concrete and steel. And if you read through it, it's a lot of fun. It will tell you why we have come this far, we have this formula. And it will give you the sense that it's just approximation. Really. And sometimes it's just people, okay, we need to fix this because we have done this for 50 years and, we don't have any problem with that limit. That limit doesn't actually occur with the hot roll, so they fix it. And when you read it, you know the history behind it, you have a clear understanding of what has become something like this. So you feel like, oh, we could talk to the structure now, like that. Okay, but now CV2, it's the old formula with another limit and with another CV. And I can tell you that this is linear, that is quadratic. So for CV1, it's just nothing like this, just this and that. But for CV2, it's this, that, and that. Okay, and then that's it. So, oh, we have that. This is also new. If you use the single angles and T's and box sections to carry the shear, you're gonna have to use CV2 now, which is actually the same CV. And I don't think, for at least I can say for the hollow steel section and box that you're not gonna have any web that is beyond the limit. So the basic calculation should be the same because kV is also 5, but for the angles and the T's, kV is 1.2, so the limit is pretty low. But then again, we don't use angles and T's for moment, right? Seems rather weird. But if you come across that, that's a problem. And now a little bit of the comparison with AISC 89. In 89, they show you this value right away, if you are familiar with it. But in the latest version, they sort of take kV out of this and put it back into the square root. And that's all. Okay? So I have the summary here for you as well. The new CVs and then the old CVs. Okay? In the old days, they have these three, and now they have this and that. Okay? So it's just the summation. Now, introducing a few more things about the beam is that when you take care of the beam, the concentrated load or the point load can become an issue for your beam. Because when your beam has a point load acting on it, rather turn this off, okay? If the point load is so large, this point load will cause moment, it will cause a shear, and it can also cause the local failure underneath it. Okay? So when you have a situation like this, you need to make sure that your beam will survive bending, flexural shear, and local failure. Local failure. And generally, the local failure that can occur is web building and web crippling as listed in the slide. Now that I'm here, I might as well draw a picture about it. No, we cannot have a load like this in real life, right? The load doesn't come with the size of a pin. It comes with some size. Let's say this may be the column, the small column that the beam support, or it may be the support itself that creates the point load back to the beam. But anyhow, it has to have some kind of dimension. So when we look at this dimension, let's say I'm going to exaggerate this. It may come in the form of the column here. The important distance here is this one. They used to call it N distance, but now they change into LB. Yeah, why? I don't know. LB. LB now. It used to be an N, but now it is called LB. And when we consider this, if it is a web yielding, the failure will occur at this region like this. So it's LB plus some distance. Okay? And the distance that you should know is this one. This distance from the end of the flange down to the end of the fillet here is called K. Again, all the K's are available in the table. But K itself is equal to the thickness of the flange plus the radius of the fillet. That's a K. And the failure will occur right at the end of the fillet here. So, for example, if it's a web yielding, if they use the slope 1 to 2.5, so if that is equal to K, this becomes 2.5 K. And that's another 2.5 K. That's why when you look at the formula, you will see LB plus 5 K. For the concentrated load, which is the typical, the official name, we can call it point load because it's short and sweet. If I have to say concentrated load all the time, I'll go crazy. Say concentrated, 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 concentrated load. Very, very difficult and tiring. Okay? And this is for this. And if the point load is at the end, you may have the stress distribution with one side of 2.5 K. So that's why you have 2.5 K plus LB in another formula. Okay? All right. Any question, ladies and gentlemen? Even if you want to ask something, you just keep it to yourself. I want to go home, man. Can you just finish it, please? No more questions, Your Honor. We just want to go home. Okay. So that's a formula for, the estimation of the web local yielding failure and web crippling. And the LB is the distance that I already showed you. And K, and web crippling, this is crazy formula. It's just the only formulas that I think they should change because this is purely curve fitting. Okay, so we have the formula for point load in midspan, where you have bigger area to contain the load, and you have the formulas for point load near the end of the beam, where you have less area, and therefore the formula is smaller. And like this is pretty clear as well. And here we have another scenario here where phi is equal to 1 and factor of safety is equal to 1.5. This is because generally they were looking for web crippling, but they found this as well. So web yielding is pretty certain and they're pretty sure about it. That's why they use phi equal to 1. Okay, that's the true reason. If the beam does not survive those point loads, we need to add bearing stiffeners to it. Okay? And the bearing stiffener, it's not very difficult to design. And, in this country, you would often see bearing stiffener all the time, because I think first of all, people don't know how to handle the point load. So whenever they have the point load, just add bearing stiffeners. That's it. No problem. No questions asked, right? Let's go home with bearing stiffener. No more. But if you don't want to go home, you just need to calculate this and see if your beam can survive the point load. If it can, you don't need bearing stiffeners. If it cannot, you need to design bearing stiffeners. And I generally calculate that, and the beams, I don't use bearing stiffeners. And I remember the fabricator asked, "Are you sure?" I said, "Absolutely." And he said, "Good, because at least we base this on calculation and everything, just not just feelings, right?" And say, okay, that's fine. But if you want to calculate this, it becomes one column. And with one rule is that you need to have the bearing stiffener that has to be stretched to the almost the end of the flange. Okay, so if I draw the top view of the beam, and you can see the web with the dotted line, when you need to have the bearing stiffener, it has to be extended near the edge, like that. Should be the dotted line as well. So when you look at this cross section, it looks like this. You need to clip it because it won't fit in because of the fillet, right? Like that. Need to be very, very near the edge, otherwise your flange may buckle. Okay? So when you have that, this is like, a column with the cruciform. Or if you have the bearing stiffener inside, your cruciform looks like this. With this is equal to, you can use the help from the web a little bit. This is 12 TW, and if it's inside, that is 25 TW. And you check the strength of this column. Okay? And this is when your K over R will always be less than 25. Because it's just very one small and bulky column. And K can be used as 0.75 as said in the slide. All right, I think that's the end because next slide is the example. Yes, right, yes. We're almost there, and we can take a quick look at one or two examples, and then if you have any question, then we can just, yeah. All right, so 10 more minutes maybe? And then we are off the hook. Okay. Why? Oh, I see. That's why. Now, it's just the example that I set up to show, demonstrate the behavior of the beam in many cases. Now, let's say it's a steel beam with a concrete floor, and that's a one-way slab in that direction. So that means B2 should be automatically braced by the concrete floor. And likewise, B1 as well, right? Because you have the concrete floor on the compression flange, and your beam cannot dance. The lateral torsional buckling will not occur in neither B1 nor B2 because of the automatic brace they receive from the concrete floor slab system. But again, that means you cannot just put if this is a hollow core or the plank, you cannot just leave it on your concrete beam. You need to provide at least some kind of a interlocking system, right? Otherwise, your floor can move. So in general, the way they do it, they would provide some kind of dowel running on the back of the steel beam, and that one should automatically help lock your beam from moving sideways. So that means your beam will be fully braced. So that's the case for B1 and B2. Banana in pajamas, right? B1 and B2. B3, for example. What's another microphone? There. B, B3, for example. This B3 supports B2. So in turn, it means that B2 can help prevent B3 from moving sideways. And that also means the unbraced length of B3 becomes 1.5 meters. Right? Beam B3 can dance, but with the unbraced length equal to 1.5 meters. Now, B4. This is the opening created for demonstration only. B4 supports B1. So that becomes the unbraced length there, and that is the unbraced length. However, the biggest unbraced length is between the opening. So it is highly likely that for B4, this will become our primary concern. The unbraced length 6 meters, right? But we're going to have a help from CB. Don't forget that. For B1 and B2, it's fully braced, so we don't need to calculate for CB because they're going to reach MP for sure, right? All right. Now it means that when I want to design B1 and B2, I can just calculate the moment and calculate for the plastic section modulus right away because they will reach MP without a doubt. Okay, so I can just, I make the case to compare the ASD and LFD, but you will know that you're gonna get pretty much the same section here. So if it's ASD, the calculation of the uniform load on B1 is based on the tributary width, which is 1 meter, right? And date load is 400, live load is 800. So that means the load on the beam B1 is 1200 multiplied by 1. For LRFD, it's 1.2 multiply date load plus 1.6 multiplied live load. And I'm just making a case here that if you use 1.7 and 2.0, it doesn't conform with the concept of ASD and LIFD with the magic number 1.5. You know, the Department of Urban Planning actually wanted to incorporate this into the steel design. But Ajahn Anek asked me one day, and I said, this is the concept behind it. And he fully grasped it, and he told them, you can't do it. That's why I still think, that's why I think we still have only ASD for the steel in the ministerial regulation, which is good. If you just increase the loading side without doing anything on the resistance side, that's inconsistency. That's bad. That's not engineering. And that's using the personal feeling. Not good. Okay? So, see, now if I use this, I calculate the moment, that's the WL square over 8. And then from this formula, I didn't show it there, so let me write it here. It's WL square over 8, right? That's the moment. And it should be less than, if it's ASD, this is MP. So this is equal to Fy Zx over factor of safety. So I can use this to calculate the Zx that I want, right? So the Cx must be greater than WL square over 8 multiplied by factor of safety over Fy. Okay? Excuse me. We are done here. All right. So that means I can go on. This is the factor of safety and Fy here. Okay. Zx becomes 360. And for LIFD, I got Zx equal to 352. It's pretty much the same, right? So we probably end up using the same section. But if you use that 1.7, 2.0, whoa, it's 456. We should mention that. Okay? All right. So I can select the section from the table, make sure that my plastic section modulus exceeds that number. It's 366. I love to cut it close, It's kind of fun. And after I have the section, I better check local buckling on the flange and the web, making sure that both my flanges are compact. But actually one flange, right? Because only one flange is under compression. So I should say the compression flange is compact, and my web is also compact. So that means I can achieve the maximum moment because the beam is sufficiently braced, and I am going to reach MP. So again, including the weight of the beam in the calculation a little bit, I recalculate the moment, and this is again the strength I use. This is Fy multiplied by Zx divided by factor of safety. Oops, 1% over strength. I can assure you this is not the same problem as the exam that I gave the students last year, but just a coincidence. 1% over strength. I'm not going to lose my sleep over this. I'm fine. So I'm going to use it. If you ask me if I face a situation like this, will I use it? I definitely will. Okay? In LRFD, again, it's the same method, but the calculation is slightly different. So in terms of LRFD, it's safe. Because when you compare the live load over dead load ratio, it's less than 3, right? It's less than 3. So it just, it gives pretty much a similar number. So for LFD, it's perfectly safe. For ASD, it's a bit overstrength, but that means, should be okay. A little bit for the shear, The shear from the beam, it's just simple, WL over 2, that much. And I have my section, so I check my H over TW ratio. See, it's less than that limit. So I can just use the factor of safety equal to 1.5 if I want. I don't have to. Even if I don't use 1.5, you see, I have a lot compared to this. So shear is never really a problem, right? So that's one example. B2 is pretty much the same as B1, so let me skip it. Because I want to show you B3. B3, let's say if why do I do this? Hang on a minute. Actually, I don't need CB at all. I only need CB if I don't consider that B2 is bracing this. But I don't think so, because let's skip to this. See? LB is 1.5 meters, which is less than LP of the beam. So I actually don't need to calculate CB if I check this first. But if I want to calculate CB, this is how I do it. I need to break the bending moment diagram in this 1.5 meters region into 4 different, quadrants. And I need to calculate MA, MB, and MC here. And that is my M max. And why I calculate the CB in this zone? Because you can see for this, even though the unbraced lengths are the same, but here the moment is a bit less, and the moment gradient is greater than here, which is close to a straight line. When you have a bending moment diagram close to the straight line, it means that your moment does not fluctuate very much, and your beam will become easier to buckle, as you can see from the CB value. See, it's very close to 1, because this is almost a straight line. If you want to calculate the moment gradient here, it's going to be much larger than 1.1. So I just checked it, but in the end, I didn't need it. LP and LR can be obtained from the table, or you can just calculate it. So let's just skip that. Wow. Yeah, I've done that all for you. No? And again, we don't need that. And we can just check the shear later. Okay? We can shear is pretty normal. Okay, the last one, this is the interesting one. Because now we have B4 with the unbraced length of 6 meters. So we're going to go beyond LP for sure. Because LP is no more than 3 meters. Okay? It's always 1 or 2 meters something. So I go ahead and calculate CB. My maximum moment is there, so that's M max. That's M max. This is moment at a quarter point, which is that. This is moment at half span, half unbraced length, which is that. And then at 3/4 that. So I got CB as much as 1.57 because of the stress gradient. Okay? Now, for this, I try this beam because the problem with the design is that you don't know. There's too many unknowns, so you need to try the section. You can try to approximate this, but you know it shouldn't be that difficult. But I'm trying to create some design tables with SYS, and it should become available maybe by the end of this year or early next year. That the table should contain, you know, the flexural capacity for every beam for many unbraced lengths. For example, if the unbraced length is equal to 2 meters, if you use this section, how much moment it can carry? You can just pick it off from the table right away. It's under development. Actually, I got most of the numbers done, but they want a graph. No, I don't have time to create a graph just yet. Anyway, let's say we pick this section. And the unbraced length 6 meters is even beyond LR. So that means we are now in the elastic region. Right? So we need to approximate the strength of the beam in elastic region. You can pick the J from the table, or you can calculate it. You can pick the H0 and CW from the table as well. And now you just need to plug those numbers into this. Now for the H shape, the doubly symmetric C is equal to 1, and I use CB equal to 157. So I have the moment that much. Okay? And MP is 17,900 kilogram meter. And after including CB here, I have the moment almost equal to MP. It's just slightly short of that. And for LIFD, it's just, you know, different calculation. But this moment is greater than that, way greater than that, because of CB. If you take 1.57 out of this, how much do we get? I wonder why I didn't do that. So let's say I have 96,000, which is still greater than that, you know, moment, which means I need to redesign this beam. It's too big, right? At least in terms of strength, but that's just, you know, let's say it's for demonstration. And that's how we can use CB. In this case, I just realized that the beam is too big, so I better reduce it next time. And we have the example of the calculation of the plate girder as well. Let me just go over this quickly because it's just how we can say design the section, I suppose. We have the preliminary section based on the moment, and then calculate the section properties and come back and calculate LP and LR. Yeah, I want to show you how LP and LR are calculated for the plate girder. After we have the cross-section properties, the RT can be calculated by using this formula, which is from the specification. You use this after you have the section, you have RT, and then you can calculate LP and LR, and then this is how we calculate the strength of the plate girder. And this time, I believe if I don't use CB, we're not going to pass it. Okay? And again, CB is calculated as before. I don't have the moment diagram, but these black spots mark the mark the bracings for the beams. So we have the unbraced length of 9 meters here, but the moment gradient here is bigger than the moment gradient here, which should be close to a flat line, but the unbraced length here is 4.5. Okay? So this is the CB for the 9 meter unbraced length. Let me draw the picture for you. For this particular beam, you know, the bending moment diagram should be somewhat close to this, right? And we have the unbraced length, 9 meters here, and then 4.5 meters here. That's also 9. Right here, CB is going to be large, and after the calculation, we know it's 1.57. But the unbraced length is 9 meters. Right here, it's almost a flat line. I don't need to calculate CB at all. I would just assume CB is approximately 1. But the unbraced length is 4.5 meters. And we need to check both cases. Okay? Because this one, even though the unbraced length is small, but CB is 1. In this case, unbraced length is large, but so is CB. So we can tell right away which case is going to govern our design. So we need to check both.